The monoplane is an aircraft with a single main wing, giving it a simple and relatively light structure, which reduces drag and makes it efficient for many aircraft. Its main advantage is lower weight and good aerodynamic efficiency, while its drawback is that it offers less lifting area than multiple wing arrangements, and it is also easy to maintain. The biplane is an aircraft with two main wings stacked vertically, allowing a large lifting area within a compact span. This gives it good low-speed lift and strong structural support, but the close wings interfere with each other aerodynamically, creating extra drag and limiting its efficiency at higher speeds, and it suits low-speed aircraft. The multiplane is an aircraft with 3 or more stacked wings, using several surfaces to produce substantial lift from a relatively small wingspan. This can help with low-speed performance and compact designs, but the many wings create interference and drag, making the arrangement inefficient compared with modern monoplanes. In practice, the low wing is mounted near the lower part of the fuselage, giving the aircraft a clean upper surface and often improving high-speed aerodynamic performance. It also makes landing gear and fuel systems easier to package in some designs, but it can reduce downward visibility and place the wing closer to debris and ground hazards. The mid-wing is attached around the middle of the fuselage, giving the aircraft a balanced aerodynamic layout and keeping the wing close to the center of mass. It can provide clean airflow and good maneuverability, but the wing passes through the fuselage structure, making internal space and construction more complicated, and it helps with balance. The high wing is mounted above the fuselage, giving the aircraft strong stability and a clear view below the wing. This arrangement is useful for transport, utility and observation aircraft, especially on rough surfaces, but it can add structural complexity and may produce more interference around the fuselage and wing roots, and it suits utility aircraft. The parasol wing is positioned above the fuselage and supported by struts or other external structure, placing the wing high without attaching it directly to the cabin. It gives good ground clearance and visibility below, but the supporting struts add drag and weight, reducing the aerodynamic efficiency of the overall aircraft, and it was common early. The straight, tapered wing uses a mostly straight leading edge, or gradually narrows toward the tip, providing predictable airflow and simple construction. Straight wings work well at low speeds, while tapering can reduce drag and weight, but neither is ideal for very high speeds, and both can require careful design to avoid tip stall problems. The elliptical wing has a planform that closely follows an ellipse, distributing lift efficiently along the span and reducing induced drag when designed correctly. This can improve performance and handling, but the curved shape is harder and more expensive to manufacture, and it offers little practical benefit when simplicity is more important. The swept wing angles backward from the fuselage, reducing the airflow component acting directly across the wing and delaying compressibility effects at high speed. This makes it useful for fast aircraft, but it also reduces low-speed lift efficiency and can increase stall speed, requiring more careful takeoff and landing design. The forward swept wing angles toward the front of the aircraft, allowing useful maneuverability and keeping the wing root away from some airflow disturbances. It can improve control at high angles of attack, but aerodynamic loads tend to twist the wing upward, creating structural challenges that require strong and often heavier construction. The delta wing has a broad triangular shape with a large swept leading edge, providing strong structure and useful performance at high speed. It can generate lift effectively at high angles of attack, but its large surface and high sweep can increase drag at low speeds, often requiring higher approach speeds or special handling techniques. The variable sweep wing changes its sweep angle during flight, using a more extended position for slower speeds and a more swept position for high-speed flight. This gives one aircraft a wider performance range, but the hinges, actuators and reinforcement add weight, cost and mechanical complexity while reducing useful internal space. The dihedral wing angles upward from the fuselage toward the tips, so a disturbed aircraft naturally tends to roll back toward level flight. This provides useful lateral stability and can make handling easier, but too much dihedral can reduce roll responsiveness and make the aircraft less agile during deliberate maneuvering, and it favors stability over agility. The anhedral wing angles downward from the fuselage toward the tips, reducing the natural rolling stability created by conventional dihedral. This can make an aircraft more responsive and can compensate for highly stable layouts, but it also demands more active control and can make the aircraft less forgiving when disturbed, and it suits aircraft with high stability. The gull wing bends upward near the wing root before extending outward, creating a raised center section while keeping the outer wing at a useful angle. It can provide ground clearance and favorable structural geometry, but the sharp change in shape complicates construction and can create uneven aerodynamic loading across the wing. The inverted gull wing bends downward near the fuselage before rising toward the outer sections, allowing a shorter landing gear arrangement while keeping the propeller or wing clearance useful. It can also improve structural packaging, but the complex shape adds weight and construction difficulty and may create more complicated airflow. The tandem wing uses two main lifting surfaces placed one behind the other, allowing both wings to contribute to lift and giving designers flexibility in balancing the aircraft. It can provide good control and efficient use of the airframe, but the rear wing operates in disturbed airflow from the front wing, which can reduce overall efficiency. The canard places a small lifting surface ahead of the main wing, allowing it to contribute lift and pitch control while changing how the aircraft behaves near a stall. It can improve maneuverability and reduce some trim losses, but the forward surface complicates stability and airflow, requiring careful control of the aircraft's center of gravity. The flying wing removes most of the conventional fuselage and tail, using a large integrated wing to generate nearly all the aircraft's lift. This can reduce wetted area and improve aerodynamic efficiency while offering useful internal volume. But stability, control, pressurization, and payload integration are more difficult than on conventional aircraft. The joint box wing connects the upper and lower lifting surfaces at their tips, forming a closed structure that can reduce some induced drag and provide high structural efficiency. It can achieve useful lift with a compact span, but the unusual geometry complicates construction, control surfaces, maintenance, and integration with engines or other systems. The braced wing uses struts, wires, or other external members to support the wing and transfer aerodynamic loads into the airframe. This can make the wing lighter and structurally efficient, especially at low speeds, but the external supports disturb airflow and create additional drag, which becomes increasingly costly as speed rises. The cantilever wing carries its main structural loads internally without external struts or wires supporting the wing from outside. This produces a clean aerodynamic surface and reduces parasite drag, making it well suited to faster aircraft. But the internal spars and reinforced structure can add weight and make the wing more demanding to design and build. The oblique wing rotates as a single wing across the fuselage, using a low sweep angle for efficient, slower flight and a highly angled position for high-speed operation. It offers a way to cover a broad speed range, but the rotating structure introduces major mechanical and aerodynamic challenges, making the concept difficult to implement. The morphing wing changes its shape, camber, sweep, or other geometry during flight to adapt to different conditions. This can improve efficiency across a wide range of speeds and maneuvers without relying on one fixed shape, but the mechanisms and flexible structures add complexity, weight, and maintenance demands, while reliability can be challenging.